Hello, good evening, Naina. Do you hear me? Can you hear me?
Yes, sir.
Great. So I will wait for a couple of minutes. Hello, Daniel. Good evening. How are you?
Good. How about you?
Yeah, great. Nice to hear from you both. And also, Edward have joined us. Okay. So let's start our lecture today. So we will continue in Simplex method sensitivity analysis. Okay. So we will continue using the same problem. So I will introduce it again. We have a maximization problem. We have 3 decision variables and we have 3 constraints. So we have reformulated the problem into its standard form, and there was no surplus variable. But if you, in case if you have a minimization problem with a surplus variable, so the first thing is you're gonna change the minimization problem into maximization by multiplying the state variable coefficient by minus. So if it was minimization, so it will be z equals minus 110 by x1 minus 120 by x2 and minus 150 by x3. For the constraints, so you're going to multiply both sides with negatives, so this will be changed into more or equal, and the quantity will be in negative. This is okay for MATLAB. Then you will only have in this case an s. You don't need an artificial variable in this case. So this is the built-in code for the MATLAB. I just only add the final line over here. So because MATLAB doesn't calculate the slack for you, so basically it's only simple way. So you have the right-hand side, which is stored in B matrices, which is the right-hand side. Then you subtract it with your technological matrices multiplied by your x's. This will give you the slack variable. And also we have seen what the cases we're gonna cover in this semester. So we will have the range of the optimality for the objective function coefficient when we don't have the non-basic, which we covered the last lecture. Then we will have the range of the optimality for the objective function. So it might be profit as a maximization or cost for minimization, or maybe you will have another kind of a problem. So this time we will try to do for the basic solution. So this is the general formula. So you can reconstruct the whole simplex matrices in any iteration, but this is one is the optimal. So for example, you can reconstruct the same matrices for the first iteration, but this time the values for the CV and B and AJ and NCV will be changed. So for example, if we want to reconstruct the same matrix here for the first iteration, so CV will be zeros because they will be dedicated for the slack variables. And B inverse will be the identity matrix. So then you will have the other values fit in here. So x1, x2, and x3 will be the non-basic, and we will be denoted in the left side of the matrices. And it will be the same. By the way, for this line over here, for example, for this line, so you can extend the same equation for the basic solution. So you can extend it up to here, but there is no need for this column to be filled with the same equation, because basically eventually we'll have the zero for them. And also it applies here. So basically this equations, you can extend AJ to cover this area, but if you have the basic solution, you will retain the identity matrix. And also we have mentioned for alternative solution, So you will consider all alternative solution are non-basic unless you have resolved the problem and you add them into your left hand side to be the basic variable. So this is the same matrix we have used in the simplex form, but it is done in matrices. So let's go to the second case. When you have the range of the optimality for the objective function for the basic solution. So assume this, like your manager want to increase the price for the second product or the third because he's satisfied with this matrix. So like when we have this optimal solution, let's assume this in this scenario, he says my goal wasn't to earn this amount. I want more since x2 and x3 are productive. So he's kind of greedy in this. So or maybe he's looking for selling more items. So maybe he's thinking to reduce the price. So does he should stick with the same production plan? So we know the production plan is basically the final iteration for the simplex method. So the governing equation will be this line. So CV by B inverse by, so over here you will put the matrices for the technical coefficient for the non-basic solution. So here it will be AXV, okay, minus NCV. So right now we're still having X1 and S1 and S3 as the non-basic. So as this matrix is more or equal 0, so we still keeping the optimal solution. So regardless the amount he changed the price in C2 or C3, the coefficient for the basic solution. So if we go back to the original matrix, so regardless he changed this amount, so like for example if he changed it to 140, this one maybe for 200, or he might be thinking in different scenario. If they are still within the same range, so the only thing will be changed is the value for z, and else matrices will be remain the same. So you don't need to recalculate the whole body of the matrix. So you don't need to recalculate everything here. The only thing you need is to recalculate the value for z if these are within the range. So let's see this example. For example, so he want to change the value for C2. You can do it for C2 and C3 simultaneously, and also you can do it for C1. So you can, for example, make a combination for the range of the optimality for the objective function, regardless if it was basic or non-basic. You can do that, but the main difference over here is it will be a case-based sensitivity analysis. So you will not have a range, for example. You just try to resolve it for this scenario. But like if we don't, we just only consider a one variable at a time. So you need to fix C3 at original amount, then find out the objective function range of optimality for the second product. So you cannot change them, both of them at the same time, because you need more matrices. So the manager is considering to change the price for the second product. What is the range of the optimality? So regardless, I give you the second question and the third, you need to find the range of the optimality in the first place. To see, for example, if it was within the range, so the only thing I need to recalculate is the objective function z. But in case if it's out of the range, so then I need to reconstruct my matrices and see if it's optimal, then reiterate again from the place I have stopped. So what is the range of the optimality? So we have learned it should be using this equation. So simply you just need to put the same matrices, you take it from the original matrix over here. So you can take all the values from here and then just uh, make C2 as a variable, then add C3 values, then you will have a multiplication matrices. So you know the multiplication for a row by column. So you will multiply C2 by 2.5, then 150 by minus 1.25, then 0 by this one. So minus 1.12 will give you this equation. Then you will redo it again. So this
I have
row,
I have I have a question about
yes.
that equation and the one on the last slide too.
Mhm.
Um, is the 12.500 supposed to be a column, or is that not supposed to be a multiplication factor?
Yeah, it's supposed to be negative. Yes, you are correct. Thank you for
Then the second question is,
this is negative. Yes, thank you.
where is AJ?
So for here, basically for AJ, if you still in this area, so this one will be the technical coefficient for the non-basic solution. So this matrix over here, you can substitute it by AVJ, this one, AXV, this one. But if you like, you can continue this one, but you don't need to recalculate this matrix because eventually this is will be always zero. So here it will be like if I want to put it here, so this matrix basically will be CV multiplied by B inverse multiplied by B minus CV. So when you take a look to this matrix, so B inverse by B will be the identity. Then any matrix by the identity will be CV again minus CV. So this is will be eventually zero. But we don't need to recalculate this thing because eventually we know this is gonna be nullified. So we will put it zero, uh, like in advance. So like we have a less calculation, and we have said before, the matrix-based simplex is to make a lesser calculation than what we have done it in big M and two-phase method. And also it's yeah.
My question was more of where is it in the numerical equation you have down there? Is it part of that matrix?
Okay.
Is that matrix B inverse times AJ, or is that matrix just B inverse?
So you, B B inverse is the technical coefficient, the inverse for the technical coefficient for your basic variable. So you will name it in the first solution here. So here, when you take this matrix, for example, so then you will reformulate it in a standard form. So B will be 5, 5, 2. Sorry, so since we had taking x2 and x3, and we know s2 was the one of the basic solutions, so it will be 3, 2, 0, because in the first line we have plus 0 as 1. Then for the second line, it will be 0, 3, 1, because here we have the coefficient. And the last one will be 1, 2, 0. So this is the B. Then you will take the inverse for it, only for this B. For the other matrix, the accumulated one, which is the NXV, so it will be start with 5, 1, 0, then it will be 5, 0, 0, then eventually will be 0, 0, 1. And it's here. So you can see this is the MATLAB code. So they are stored here. So you know, you notice here what you're considering are the basic solution for this iteration. So this is XV, which is contain X2, X3, and S2. Then we have the non-basic matrix, which include X1, S1, and S3. So here we have the CV, which is 120, 150, and 0. Then we have the non-basic solution, NCV, which is 110 for X1, then 0 for S1, and 0 for S3. We have the matrix B. So this is B, which is 3, 2, 0, 0, 3, 1, and 1, 2, 0. Then we have an AV or an XV, as I mentioned it before. So it will be 510, 500, and 001. And you have the right hand side is stored in B matrix. So this is 100, 120, and 70. So basically in any iteration, so let's forget about we are just only solving the sensitivity analysis, like you are solving in any iteration in the beginning. So you're gonna change XV. So this one will be S1, S2, and S3. Then NXV will be S1, will be X1, X2, and X3. Then you will change CV. So in the first iteration, there will be 0, 0, 0. And the NCV will be 110, 120, and 150. And the same applies for B. So B in this case will be the identity, and NAV will be 532, 503, and 012. Then but the right hand side doesn't change uh, regardless the iteration you are, like for example for the first iteration will be the same for the second. So this one will be remain the same variable over here. So what we have done here, so for this one, so you're gonna see what makes this solution optimal. Okay, so we want to see what makes this solution optimal. So we have some constraint or some restriction. The first thing, this line over here should be more or equal to 0. If it's equal to 0, then we know it's reached the optimality. So mostly it will be a basic solution unless we have a degeneracy or alternative. So it might be something like that, but in general, we are just looking for this one. So we might be finding something here, zeros, but in general, we shouldn't have any negative value over here. So this is will reserve our optimality condition or the post-optimal condition. The second thing, this one also, this guy should be more or equal to 0. So because if you have any negative number over here, so you will create a duality, which we will didn't cover yet. Hopefully we will cover it next lecture. So this one also reserve our optimality condition. This is like I cannot do anything with this one. So that regardless the value over here, it doesn't say this is an optimal. So it can be 0, it can be any number over here, and also this matrix over here. So there is no restriction over here. These matrices by default, if they are the basic, so this one will be 0j. So like for example, you have 3 decision or a basic solution, so will be 3 zeros. 4 will be having 4 zeros, and this will be the identity matrix equaling the number of a basic solution. If you have a 3, so this is will be a 3 by 3 matrix. If you have like a 12, so then you will have a 12 ones. So the thing over here we're trying to do is, instead of recalculating everything from the beginning, we just like see, for example, you know what is the optimal solution, and then you want to have only single change, like you want to change something and you see if this still optimal or not. So this matrix should be more or equal to 0. And in some sense, this one will be always the NXV, this matrices. If you stay in this column over here, but it can be generalized for here, or even it can be generalized in one of the columns, and we will see later in other sensitivity analysis parts. Is it clear or?
My question is more of that matrix of numbers right there you have in the equation. Is that A star or is that B inverse?
So this one is A star, which is the multiplication of B inverse. So
in the work down you have there in your inequality,
okay,
where you're actually putting numbers in. What matrix is that?
yeah. This one should be AG, not AG star. This one you are looking here, because you're gonna multiply both of these. If you multiply then you will have the A star over here.
the next question is, you have a row vector, in a row vector equation there, inequality with a column vector. Why?
Here in this line.
Yeah, why is it a row vector on one side and a column vector on the other?
You can say it is like I am saving some space, so should be the same thing over here. So it should be like also a row, not a column. So I'm just like saving the space for this one. Sorry for that. Okay. So you're gonna make only simple multiplication. So you're gonna multiply this with this row with this column. Then you will do it again. So when you multiply C2 by 2.5, then 150 by minus 0.15, then 0 by 8, so minus 112, you get this equation. So simple linear algebra, so because this is in the right hand side, then you put it in the left hand side, then you divide both sides with 2.5, so then you will put C2 is more or equal to 120. Then you have the second equation again, so you will pick this one again and multiply it over here. Then you can have the same thing here, so eventually C2 should be more or equal 75. And then you will do it again for the last row. Then you will have C2 is less or equal to 150. So then you will have draw a line to know what is the range, because for example C2 is more than 120, then you have this C2 is more than 75. So what is the logic can combine of these two uh, rules over here? So we should have combined rule for them. So we know from, for example, sorry, this is a typo. So from 75 to 120, so it's only applicable for this line. So we cannot take this area. From 120 to infinity, so we have a god until we reach 225. So any number less than 225 is acceptable. So the range is between 120 and 225. So like I have created for you a MATLAB code for it, so you can try it out. So you can just run the code and manipulate some values over here, so then you will have the same equations. Okay. So we know the range is between 120 and 225. So let's say about the second and the third question. So the second question says, if the marketing department proposed to increase the price to 125, so what will you include or you will consider this type of so what will happen? And also the production engineer recalculated the cost and found the net price for the second product to be 105. So what will done in his production plan right here? So in case uh, of having 125, so 125 lies within the range of the optimality over here. So no change. So you just need to recalculate Z as I mentioned. So Z in this case will be equal to 6,000. So like there is nothing to rush to change all these matrices, only you need to change this guy. For the second questions, it says, if I have 105, so what will happen? Okay. So if the change isn't within the range of optimality here. So what's will happen to your matrix? So then you will copy everything. So there is um, nothing changed for these matrices. So B inverse by NXV will be remain the same. The identity matrix will be remain the same. Also, your solution will be the same. So the values for x2 and x3 and s2 will be reserved. But the only thing will be changed is this line over here and also the right hand side. So here I don't want you to exhaust it, so you don't need to do anything. Even you can put it a question mark over here, but basically there will be 0. But the only thing will be changed is over this line and the z value. So the thing here, when I use the same matrix, so if I use this matrix again, but instead of 120, the only thing I need to is to put 105. Okay, so the same thing will be happened. I will show you the MATLAB code. So here we have the MATLAB code. So this is the matrix B, which will be always remain the same. So then we have CV over here. So CV is have been changed. So we have 105. Okay. So the else matrix, I will not change it because we considering this one is still optimal. Okay, if it's not optimal, so then you will need to update some columns. So basically, you will update CV and CV and B and NAV. So you run it. So so this is the matrix H1, which is the B inverse by NAV or NXV. So it's remain, by the way, the same. So there is no change, even though you can copy and paste it over here. Then we have the range of optimality, which is reserved in H2. So the value is minus 35, 15, and 60. So we didn't need to extend it, so we know it will be 0 and 0 and 0. And also the values for your basic solution will be remain the same. So no change over here, but the z value will be changed. So you can fill this one into your matrices again. So you will fill your matrix again. So you will notice the change is only over here and here. So like when you use the MATLAB code, if you forget the referencing, I have put it in this slide. I can show it to you here. So here we have H2, here we have H1, we have here H4 and H3. So when you run the program, for example, I will go back to the MATLAB code. So the only thing here is you need to update these matrices, then you will have the values for H1, H2, H3, and H4. So depending on the problem, maybe not all of them will be changed. So take this matrix as a reference. Okay. So here, when you reevaluate this one, so basically, what is this tell you? This tell you X1 should be included in the production line because I have changed the value for X2. So the profit for is what is the logic behind that? So X2 was 120. So this is the profit come from X2. When I decrease the profit to 105, and X1 originally was 110. So the Simplex is thinking, yeah, maybe X1 right now, it's time for X1 to be introduced into the production line. So maybe I'm taking X1 in consideration. So it might be replacing X2 or substituting X3, or maybe I should utilize more resource from us too. So then here you're gonna divide. So you can iterate the same thing. So you're gonna divide 15 by 2.5, or 27 by minus 1.25, or 37 by 8.75. So there is two ways to go that. So the ratio, if you try to do it, so the ratio over here will be 6. This is negative, so I will exclude this line, and this will be 4 point something. So this tells me I should utilize the second resource more. So x1 is replacing x2. So then here we have x1, x2, and x3 as a new basic solution. So what you can do, for example, there is two ways you can do it. So the same thing, you can go to MATLAB code and just basically update all the information over here, then recalculate again. Hopefully H3 over here and H3 over here will be sorry, H4 will be more or equal to 0, and it's reached the optimality condition. So it might be not, so then you're gonna reiterate again. So you can use the matrix form to recalculate the same thing, but you need to update the all the matrices, so CV, NCV, B, and also NXV or NAV. So you need to update all these things to see if it's optimal or not. The second thing is you just use the symbol matrices. So you can, for example, just reiterate from where you have stopped. So you're gonna do the same way we have performed simplex method. So then, thankfully, you need just to do only one iteration. So we have seen x1 have replaced s2, and s2 is optimal because all of this line is more or equal to 0. So no further thing to do. So here you give your production engineer the new plan. You told him x2 right now will be 4.2, x3. So I have increased x3 but reduced x2. So x1 is taking some of x2 resources, and we starting build up x2. So this is like a compare, like was a bargaining between the three products. So I produced more x3, then reduced somehow x2 and shared some of its resources with x1, and I have this new production plan. But noticed over here, so the right hand side or the objective function is reduced. So the thing is here, when I reducing the price of x2, maybe I will gain some losses. So let's see the third range of optimality. So supposedly you are working in a production line, and then you noticed, for example, one of your resources have been not what is supposed to be. So one of you, or maybe one of your employee have been injured during the production, then you will have a less hours to work on, or one of the machine have stopped, so it's have a downtime time, or maybe you found your stock is not what it should be. So there is many scenarios you can imagine that. So let's see to what extent the final solution will be remained. The thing here, when we starting up the range of optimality, so any change in this scenario will be affecting the values for x1, x2, and x3, and also will be affecting the state variable z. So whatever you have happen in your right hand side, so there will be a affection in the state value and its decision variables. So when we look to this matrix again, the only thing can control the right hand side is this guy over here. So b should be more or equal 0 always. So regardless in which iteration you are right now, so this value b inverse by b should be more or equal to 0. So I don't use this governing equation right now. I'm using this instead in case for the right hand side. So let's consider if we found out the third one is having a problem, so let's say what is the range of optimality for this one? So you're gonna use this matrix again. So B inverse by B. So what is the B inverse? B inverse is the inverse matrices for the technological coefficient for the basic solution. So we have, sorry. So we have B over here, which is for x2, x3, and s2. So this is the line is reserved for B. So we know in linear algebra, the inverse is very costly. So it's very recommended you will save it. So when you take the inverse and you do another computation, you will reserve it in one matrices, and then you can recruit it again and again. So from where the coefficient we are taking them? So the coefficient for B are taking from the original matrix. From here. This one. So you're gonna see which variables are the basic solution. There were x2, x3, and s2. So B will be 3, 2, 0, then 0, 3, 1, then 1, 2, 0, which is over here. This matrix B. So you will take the inverse, then multiply it by B. As this equation is more or equal to 0, so then we have the optimality condition is met for the right-hand side. So basically, you're going to multiply this matrix. So you will fix the first right-hand side and the second-hand side. Then you will have the third one over here. Okay. So you will have basically three equations, because this is a row by column, then a row by column, then a row by column. Then you will have three equations including B, because half by 100, then 0 by 120, then minus 0.5 by B3 should be equal to 0. So this is the first equation. Then we will have minus 0.25 by 100, then 0 by 120, then 0.75 by B3 will be reserved in this line. So B3 eventually will be more or equal 33.3. Then you will have 0.75 by 100, then 1 by 120, then minus 2.25 by B3 will be in this line. Then eventually we will having B3 is less or equal to 86 and 2 over 3. So then you have three logics over here. So you can draw a number line over here to see like what is like make all of them logical, or if you have anything. So 100 over here starts to minus infinity. Then we have the 86 over here. So we should pick 86 because this area is not covered by this constraint. So we can neglect this area. So we will start with less or equal 86 and 2 of the third. And also it cannot go to infinity. It should be more than 33.33. So when you check up this resource, the range of optimality for it, it will be from 33.33 and 86.66. So the original resource told me, for example, I have 70 hours. So if I can reduce it between these two values, still valid. So let's assume another scenario. If it says from minus infinity to 86, it's still optimal. So this is not logical. Why? Because like you cannot imagine in a production line we have 70 hours and we can just reduce it to minus infinity. Like I am giving the employee like to take a very long rest, so they will not achieve anything. So even mathematically it sounds perfect, but in real life situation these values should be considered. So like as uh, an engineer when you are in a production line, so how many hours you can reduce this thing? So like what is the availability? Can I increase it? Let's say this is for infinity. Can I put a resource with the infinity hour? I can. So like it should be also matching what's happening in real life. I think 70 with between these two ranges is very good. But this is not all the scenarios. So let's say over here the manager is considering to change the third resource setting. So he was asked, so forget this one. So so it's he asked it to be 80 instead of 70. So this is a typo from me. So he want to utilize the resource when it's having an 80. And the other thing is when this resource is can be found 20. So what is the production plan in this case? So for the first scenario over here, so 80 is within the range over here. So since 80 is within the range over here, I don't have any change for this guy. So I don't need to recalculate this thing. The only thing is will affecting my right hand side. So all the values in right hand side will be affected. So I'm gonna use the equations again. So you can use the all equations again. So you don't need to do anything in this side, in this square. You just need to recalculate both of these two lines. So you can notice x2 is increased and also x3 because like what's happening actually. So we have 70 and then we increase it to 80. So there is 2 extra 10 hours for this resource as a 3. So then we can utilize more x2 and x3 if it's still optimal solution. So we can gain a profit from this one. How about when it's not within the range of the optimality? So if it's decrease it to 20. So can anyone tell me if I decrease the resource and let's assume this is still optimal. So he decreased it from 80 to 60. Forget it's out of range. So what will happen to x2 and x3 and x1? If it's still in the range of optimality, can someone tell me what will happen? Hello?
The value might change a bit.
Yeah, so like basically will they increase or decrease, or what is the change will happen? I'm assuming the resource will be decreased, so like from 70 it will be 60, but it's still optimal, so it's still within this range. So what will happen for x2 and x3? Are they decreased or increased? They should be decreasing, okay, because like this is the logic. For example, I have decreased the machining hour, so how many parts I should produce? Of course you should produce less parts. If I increase it, so the logical thing it says, but it's still within the range you are accepted, so then the number of parts should be increased, and this is logic should be mirrored in the simplex algorithm. So in case it is out of range, so forget about the scenario and we are saying it's still here 20. Okay, so it's way less than what I can imagine or accept. Like say like a machine has been broken, so and still I need to do something about it. So over here you're gonna recalculate everything, so this matrix will be not changing, so they are remain the same. The thing is over here, so here x3 have a minus value, and we know this shouldn't be a negative. So it's a creative problem. Okay. So how we solve this problem over here? By the way, z value is not the same anymore, but I just like put it over here because we know this matrix is not optimal. So we need to change it. So there is two ways to change it. The first thing is you're gonna use the duality analysis, which we will cover next lecture. So you will take this one as a pivot row, then you will change it in one of these with the same thing. So you will only picking the minus values, then you're gonna reiterate from this guy again. So this is gonna be done by duality analysis. Or the simple way here over here is just to recalculate the whole matrix again. So since like it's not within the range of optimality, I know I need to reevaluate this matrix again. So you can just plug the new values in MATLAB and see what will happen for it, and eventually it give you a new matrix. So let's take a look for the change of the technological coefficient for the non-basic solution. So let's imagine this scenario. You have the manager which is not satisfied with not including X1 in the production line. And he says, how about if we, for example, enhance the performance of the machine and the machines in my production line? And then let's say if I enhance it, and then it might be affecting the price. So like maybe he used one of the continuous improvement tools. Maybe he using Kaizen or Six Sigma or whatever. And he found a way to reduce the cost so he will gain more profit, and this will need a smaller rate, and this one will be smaller rate because he thinks this one, for example, I will not utilize any resource for the third machine, so it's good thing to invest in this product. So what will happen? So this is the original matrix over here, and we know x1 is still non-basic. So what will happen if I have changed the technological coefficient for x1? So so we have altered the original matrix. So this is the original matrix, and then we have this new matrix over here. So the price was reduced, so the profit is increased, so 120. So where we get this value actually? So we get it from break-even analysis. So like for example, you start using break-even analysis, then you go to Simplex. You can combine multiple methods, or even you can do some statistical effort over here or machine learning. So you know from prediction model, this is the cost or the profit for your products. Then you formulate these things the same way. So after you have analyzed it and put it in a Simplex, this is the new. So maybe you do like a plan, do, check, act, and you have the enhanced model over here. So the production rate have been changed. So B, the technical coefficient for your original basic solution will remain the same. But AXV or NVX, so the technical coefficient for the non-basic solution is changed, and also the NCV is not the same over here. So basically, this one will be changed over here. So you know, for example, this will be not optimal. So it's by case, sensitivity by case. So like I cannot put it into somehow some range because each time it will be generate a new study. So I knew x1 is not the optimal in this scenario, so everything else is remain the same. Then I will introduce the right hand side for it again. So both of these two matrices will be changed if I change any of the technical coefficient for the non-basic solution. Then I'm gonna reiterate again and have the optimal solution for it. So in case also if you change the technical coefficient for the basic solution, also it will be affecting your solution. So you need to do it. But basically, if there are a basic solution within your answer, so you don't need to enhance your model. Okay. So basically you will looking for enhancing the cost for it. So you don't need to change this one. Unless like you are, for example, have make improvement and you make the study and see this improvement was accumulative. Let's say, for example, you have balanced the line and you take some other resources over here. So eventually this was changed because you do this thing. So then you gonna reevaluate everything from the beginning. So this one is interesting. So how about the manager, for example, says we have uh, like a new product, we should put it in the line. It's X4. So to what extent this product will be changing my matrices over here? So he think this product should be included. Um, so the profit for it was 150. The technological coefficient for it was this rate, so it consumes 642 from the 3 constraint. And how what will happen for this one? So this thing is only adding a one line for the NCV and also adding one column for the NXV. So you just need to add two things to your non-basic solution. So you will not mess with the basic solution. So let's see in MATLAB how we're gonna perform it. Sorry again. Yes, thank you, Nina. I haven't seen your answer. Okay. So basically, when you have the same matrices over here, so you will not touch CV because they are related to the basic solution. So you will start up with NCV. Okay. So with NCV, you will add the new price. So it was 150. Then for B matrix, so you will not change it so ever. So it will be remaining the same. So this is the technological coefficient for your basic solution. You will not touch it at all because basically they are for the basic solution. Right now for the non-basic solution, so NXV or NAV, so you're gonna add a new constraint. So this is will be adding 6 over here. Then let's go back to the slides. I should memorize it. So 6, 4, 2. So I still have 4 and 2. I will write it in whiteboard if you still. So here we have 4 and then we have 2. And just run the program. Of course, if I messed up with the number, so by default, MATLAB will give you a red line. So you will notice you have unbalanced matrices. Okay, so the solution was optimal. So let's say. So right now, my original H was 3 by 3. You will notice it's not, right now is 3 by 4. So I have added a new column here. This is a new column. But by the way, because the solution, I don't know still if the solution is optimal or not yet. But because the basic variable was x2 and x3, so the B inverse by AJ from X1 and S1 and S3 is the same, but it's changed for X4. So I adding only this one is the new one. So this is the optimality condition. So basically it tells me right now, this is weird, but it happens. If I considered the fourth product, it tells me you should starting the first product. So it tells me, yeah, it's a good to do that, but you need to introduce the new product. So this is the value for x1 and x2 and x3 and s2. So they remain the same. So but when I reiterate again, x1 should be included, but I don't know which he will replace which one of them. The optimal solution is decreased, by the way. Okay. I know why it's reduced, because I still using the same values. So this is the thing, you should be careful. So when you update your matrix, remember to like solve each part of them separately, because I have used the previous part, so it give me the solution. So I'm gonna use it. Yeah, it should be give me the same z over here. So let's go to the whiteboard, so we know what was happening in details.
By the way, it looks like we've lost Diane.
Can you repeat again, Daniel?
We've lost one of the participants.
Okay, maybe he lost connection. The previous lecture I have recorded, and I heard from Professor Alpha that like some students have a difficulty in connection. So I'll try it out to save every lecture, and if I lost the connection again, like the last lecture, then I will record it separately. So like the last lecture, I have lost the connection in the end of the lecture. So then I have recorded separately, and it's right now in your Blackboard, okay? So I know that this is hard for all of us. Like even the professors sometimes have a problem with the internet. So we have the original problem is maximization of z equals to 110 x1 plus 120 x2 plus 150 x3, subject to we have 5x1 plus 3x2 plus 2x3 less or equal to 100. Then we have 5x1 plus 3x3 is less or equal to 120. We have 1x2 plus 3x3 or 2 is less or equal to 70, and also xj is more or equal to 0. So the manager is thinking, how about to adding a new product? So this one, so he having a new product 150 x4, and he is thinking, how about to adding, so he calculate its consumption rate, so x4 plus 2x2 4x2, sorry, and then 2x2. So this is 4, this is 2. So basically CV remains the same. So CV will be equal because I
X4?
Yes. So X4, so everything depending X4 will be included in your non-basic solution. So everything related to X4 will be considered right now out of my optimality condition. Everything else will be remain the same. So originally, the original problem says X2 and X3 and S2 are the basic solution. So X1 and S1, S3 considered to be the non-basic solution. So CV will be 120, 150. So this is 150 for X3. Don't mistake it because they are sharing the same price. Then 0. So NCV will be equal to X1, 110, 0, 0, then 150. So you're adding this new element. This is the new element over here. For B will be the same. So B, there is no change over it. So will be basically 3, 2, 0, 5, 0, then 3, then 1, then we having finally 1, 2, 0. But for AVX or AXV, NAXV, sorry for that eraser. Okay. So for NXV, so this is matrix will be changed right now. So this matrix will be starting from 5, 5, 0, 0, sorry, will be 5, 1, 0. Then I will add right now 6 because 6 is for the product 4. Then in the second line over here, I have 5, 0, then I have 0, then right now we'll add 4. Then finally, I will have 0, so 0, 1, 2, and then close my matrix. So this is the first change over here. Then I will add them into my MATLAB code. So you have these things. So B, there is no change. I have told you before, B, unless you are changing B itself, so there is no change on B, then you will recalculate everything from this beginning. So we're considering this a new product. We'll be entering the plan over here. So then you will reevaluate everything. So this matrix, when you reevaluate it, so eventually it's telling you, so it's not optimal. So you're gonna stick in this scenario. You're gonna stick with the same solution. So let's see it in the MATLAB. Maybe I have miscalculation over here because I have done it manually. Let's see the MATLAB if it says the same. So we have here the Bay remains same, CV. Then we have the NCV. So for B, we don't have any change for it. Then we have the NAV, so 6, 4, 2. So then we run it. Okay, so the same answer over here. So the matrix, I just adding this column. So this is the new column. For H2, it says I have reached out the optimality conditions, so I don't need to perform the fourth product because it's 90. So X x2, x3, and s2 are the same. So anyway, because we stuck with this iteration, and finally we have contributing the same amount of z. So in other scenario, for example, you can try it by your own. So imagine if one of these is negative. So let's say this negative 45 instead of 45. So what you're gonna do is simply you just complete the simplex method. So x4 will be considered in the production, and then you will calculate the bottleneck ratio theta. So you will see which one of these will be replacing by x4. So it might be replacing x2, x3, or you need to utilize s2 in better manner. Then you're gonna reiterate again. So you're gonna use the matrix form or simplex. Either way, we'll get the same answer eventually. Okay, so let's go the sixth one. It's kind of a tricky. So here's a bonus question. I want you to imagine. So if we add a new constraint, let's say you are in a production line and you calculate the data set, you start your model with, let's say, 10 constraint, then you noticed you have forget about the forklift. Like you didn't consider it as a resource, and you just calculate your equation, and when you validate your model with the actual real life system, it doesn't match. Then you thinking, how about reconsidering a new constraint? So what will happen if I add a new constraint? Will it be improving or remaining the original answer the same it is was? Or maybe the solution will be worsen or remain the same in the best case, or always will be remain the same. So regardless of what I ever add any kind of constraint to my equation, or it might be improving or worsening the scenario. So of course we are talking just about, yeah, yes, you got the bonus, Edward. So the answer would be B. So let's see it visually in the whiteboard. So assuming you have this model, so let's go back to understand the case in a graphical solution. So this is the good thing. The only thing we can just explain some concepts using graphical solution. So then you have this system over here, and then you have the visible region in this area. And the isoprofit line, for instance, was crossing this point. So this is the isoprofit. So when you reformulate your problem, you find out a new constraint over here. So this is constraint. In one of the cases, it might be over here. So let's say this C1, this C2. So if this constraint is more or equal, and the direction of its visibility over here, so we have invisible solution. So nothing to do actually, because it says it's very impossible to have any kind of economics when you have this kind of solution. But let's just stick with this case. So if this line is actually, for example, going through this point precisely, so then we have degenerated solution. So, and this is the best case we are like hopefully to be done, because if it's maximization a problem, so this is the best thing we can get. Let's go to the other way. So we have the visible region over here. So this is x2, this is x1, and we have here. So in case your constraint, let's say, have been here, so it will be restricting your area. And this one, so we will cover something called convex. So there is no way this solution will be better than this one, because this was the optimal one. So whatever line will be crossing over here, so anything over here, for example, will be worsened. Any point in this line will not give you the same optimal solution like this one. So like if you pick here, 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 you try it like numerically, you can do it numerically. So even with you without this constraint. So if you pick any point over here, they will never give you the same maximization. And this also applies to minimization problem. So let's go back to here. So this one line, let's say this is a constraint, a new constraint. So it might be, for example, here, this line. So we have the degenerated solution. And this is the best thing we can get. Maybe it can be here, this line. So this will not be the same. And some chances, maybe, for example, let's say this line is flattened in somehow like that. And let's assume this wasn't the optimal over here. This one was the optimal over here. For instance, let's say this was the optimal. So might we give you an alternative solution in this case? When it's alternative, so it will have the same answer, but it will never be, by the way, like you will have enhancement in your solution. So like it might be a redundant constraint. So if it's redundant, so that it will be not constraint your visibility areas. Maybe it will be invisible. So it might be creating a new visible solution or degenerated or alternative. So it will not missing one of these four options. So let's say you have considered to reevaluate your function and the answer should be remain or change. Is your range of optimality will be remain, adding this constraint or not. So the thing is different between adding a new constraint and above. You will consider the new one is within the optimal solution, so within the basic. So here, for example, when you reformulate it, so this is going to be plus S4. So you will consider S4 as a basic solution. So here, you're gonna update your matrix, and you will consider S4 as a new basic solution. So this is the biggest step. So when you reevaluate your matrix over here, so you will add only a new row over here. So you will add in a new row over here. Then you will check up the right hand side over here. So then you will evaluate it again. So let's see what's happened in this scenario. So it says S4 have a negative. So basically you're gonna use the same equations, and then you will check up the right hand side if there is any out of optimality, if there is. So like you usually look to this column or this row. If there is any negative, you know this is not optimal. So then you're gonna, from where you have stopped, you just reiterate again. So let's say what's well done in MATLAB. So make sure these are the same things. So like I need to delete the previous question. So I need to remove these values. So the best thing is you just rerun it again very quickly to see it matches the previous answer. Yes, so it's give me the same answers again, 3 by 3 matrix, so this is the most important. Then I need to add a new one. So basically this time, this is the first time I'm playing with B because I have added a new constraint which is less or equal to 50. So I will add 50 over here. So I'm considering as 4 as a basic. So I will add 0 because it contributes 0. I will not mess with NCV. So right now this need to be changed B because I have added a new constraint over here. So this is will be a new 0. Okay, so this is will be also 1, 2, 3, 4, and this will be also a 0, and this one will be a 0, and then we'll add a new line over here for it. So I will go back to Blackboard so you can notice what's happening. Then go back to the MATLAB. Okay. So the matrix I have added is 1, 2, and 1.5. 1x1 plus 2.5 x2 2, sorry, not 2.5, 2 x2 plus 1.5 x3. So plus 0 s1 plus 0 s2 plus 0 s3 plus s4 is equal to 50. So you have the original matrix CV, which was 120, then 150. So because S4 right now, we know the basic solution are X2, X3, S2, then S4. Because when you're adding a new constraint, you consider it as a basic solution. So 0 and 0. So NCV will be remaining the same. So it will be equaling to 110, 0, and 0. B will change the first time B. So B will be equal to 100, 120, 70, and 50. For matrix B over here, so matrix B is have some change. So basically we have adding here for S4 and also adding here for S4. 3 by 3 matrix will be remaining the same. So 5, 3, 2, 5, 0, 3, 1, 2, 0. Sorry, this one is 5, 5, not 5. This one should be 0, 3, 1. Then you will add this one again. So for this equation, I'm not having s, so it will be 0, 0, 0, then 1. For s is 0. Then I have here 2 and 1.5, 2 and 1.5. So this is the new matrix for B. For NAV or NXV, so it applies the same. So it originally was 5, 1, 0, but then I add the equation for S4, so 0 for S4. Then I have 5, 0, 0, and 0, of course. Then for the third equation, it was 0, 0, 1, 0, and here finally 0, 0, 0. Of course, as 4 is not here, so I can delete this one. So this one, because it will be 4 by 4, and this one will be 4 by 3. Then you plug it into your MATLAB code. So the third one, x1 coefficient was 2. Sorry, it was 1. So we have here 1, 0, and 0. For this guy, adding a new one. So it was 2 and 1.5, 0 and 1. Then you just simply run it. Yes. So after you run it, so you will notice you will have a new column only. So you will not, sorry, a new row. This row is dedicated for the S4. Then you have the optimality condition. So the optimality condition says there is no problem, but we have a problem in the right hand side. So for S4 was equal to minus value. So then you start using duality, or you can just reconstruct your matrix all over again. Okay. So any question before we end our lecture today?
For how do we change variables from XB to NXB and vice versa? Like how is that controlled in the matrix method?
Okay, so you want to change between the basic solution and
When it iterates, what equation do we use to go from
okay,
XB to XB
yeah,
prime?
good question. Thank you so much for this question. So there is two possibilities. When you know your answer is not optimal, so you need to start up a new iteration. So the thing is governing me is this line over here. So if any of these, regardless the change in optimality condition, so it might be the right hand side or one of the coefficient or a different scenario, if any of these is negative value, so I need to reiterate again. And in this formula also, so I have also the same thing here. But the difference is when I have a negative value over here, so I can just continuing using the conventional simplex method. So there is nothing ambiguous over here. So if this one, for example, -2 and a 5, then we will be pivot column. Then I calculate the ratio. I'm picking the least one and replace it. So this is the easiest way. The thing is we didn't cover yet is when we have a negative in the right hand side. So it's violate or assumption unless, for example, you allowing this variable to be negative. In some cases, but we didn't cover it yet. But supposedly it shouldn't be a negative value. So then here you're gonna use the duality analysis. So like instead of picking this one as a pivot column, you will pick this guy as a pivot row. So you'll start over here. So like you will consider these are found to be optimal, and this one is should be reiterate. Then you will pick up the least ratio. So you will divide the value over here. This one you found it over here by the coefficient. So the same way you have here, but theta will be presented in this, for example, row here. You will just only picking then in this time the positive ratio. So maybe if in this case, so you will have negative here, positive, positive, positive. So then you will replace it by one of these. So like the least ratio. Then you will iterate. So reiterate again using the same method. So for example, let's suppose this one was having the least ratio. Then this one should be 1 and else one will be 0. Then you will pick this one as a pivot row. Then you will subtract it from the different one and see if it's optimal. Right now, I don't want you to like taking too much about this case when you have a duality. You just in the homework, you just I want you to just state it, just mention that you can resolve the whole problem then again using the MATLAB code. So you don't need to perform right now any duality. Um, by the way, for the project, I don't know if you plan to do a teamwork or you just want to have an individual. Hopefully, not before the end of this week. So you should meet together and I think all I don't know if you all of you having the email. I can share the email between the students if it's okay. You can just tell me yes or no.
Yeah, that should be fine.
Okay.
Naya isn't here at the moment.
Yeah, I can tell her. Maybe she have something. And also
Only assuming Edward's here.
and I will share with you the homework right now. I have released it. So let's go back to, okay. So I'm gonna open my courses. Okay, so I have already downloaded the previous lecture, so you can see it uh, over here. Also, I will release a YouTube video for it if it's if the file is very large, so you can see it in YouTube. I will update this one. So also the codes we have used it in MATLAB is you can download it from here, and also you can go to linear prog MATLAB work, so you can see the documentation for the website. And also I have uploaded some useful YouTube videos. You can follow them, and it's basically covering all our lecture. Bear with me for a moment. So go to homework. So there is a new one. This one is sensitivity analysis. So basically only one problem with the 10 branch. So the only thing is for branch number 10. Branch number 10, I would like to see if we can start with initial solution. So how are you gonna do it, perform it using the matrix form for Simplex? So this is a tricky question. You can think about it. If you find that the solution is very hard for you, there is you can substitute it by an article. So this is article is using duality and sensitivity analysis. So this is good introduction for you for next lecture. You can review it. The submission day will be not next Wednesday, the week after. Okay.
Mm-hmm.
Okay. Okay, that's it for today. Okay, thank you so much, and take care of yourselves.
Have a good night.
You too.